If your PC seems to have a voltage problem, watch this video. Welcome to the CoreLogic Deep Dive. Today, we aren't just looking at how to build a PC, we are dissecting the architecture that powers your digital life. Many users think performance is just about buying the most expensive GPU on the shelf. That is a fundamental misunderstanding of hardware dynamics. In 2026, real performance is defined by the equilibrium between your power delivery systems, your thermal overhead, and the precision of your voltage curves. The thermal voltage synergy. At the heart of every high-performance rig in Australia, where our ambient temperatures can often work against our cooling solutions, lies the relationship between voltage and heat. Silicon is not magical, it is a physical medium governed by the laws of thermodynamics. When you run a CPU or GPU at stock, auto, voltage settings, the manufacturer, be it Intel, AMD, or Nvidia, is prioritizing extreme stability over efficiency. They want to ensure that even a subpar piece of silicon remains stable under poor conditions. Consequently, they supply more voltage than the chip actually needs to reach its boost frequency. This leads to the phenomenon we call thermal throttling. As your components heat up due to that excessive voltage, the internal logic of the chip detects the temperature crossing a safety threshold. To prevent physical damage, it drops your clock speed. This isn't a malfunction, it is a safety feature. However, it is also the primary reason your expensive rig feels sluggish in intensive workloads. By understanding that voltage is essentially the fuel and heat is the waste, we can begin to calibrate our systems for a higher baseline of stability. The power delivery infrastructure, VRMs. You cannot talk about performance without addressing the voltage regulator modules, VRMs, on your motherboard. These components are the unsung heroes of your system. They take the raw power from your PSU and clean it, transform it, and deliver it to your CPU. If your VRMs are running hot, they become less efficient, introducing ripple or noise into the power delivery. This noise can cause instability, which is why your PC might crash during a benchmark even if your temperatures seem fine. In the 2026 landscape, we focus on clean power. This involves configuring your BIOS to prioritize steady-state power delivery over aggressive, rapid-fire power state changes. By stabilizing the VRM input, we create a predictable environment for the processor. This is the first step in our methodology. It is not about overclocking for the sake of higher numbers, it is about establishing a rock-solid foundation of power delivery that allows your hardware to reach its manufacturer-rated boost clocks without crashing or overheating. Defining the performance ceiling. In this guide, we are shifting our mindset. We are moving from out-of-the-box, plug-and-play, to architected performance. Every piece of software you run, every game you play, and every render you initiate makes specific demands on your hardware. When those demands are inconsistent, the hardware struggles to adjust its power states. Our goal is to create a configuration that anticipates these demands, maintaining the chip in its sweet spot, the point where voltage is sufficient for stability but not excessive enough to generate unnecessary thermal output. In the upcoming modules, we will cover the diagnostic tools required to measure these variables with absolute precision. But first, you must understand that your hardware is a variable instrument. It reacts to your environment, your case airflow, and your specific power supply. Stop viewing your PC as a static object. View it as an ecosystem. When you tune that ecosystem with precision, the gains in frame consistency and system responsiveness are not just measurable, they are transformative. Once we understand the architecture of our components, the next step is visibility. In the world of high-performance computing, you cannot optimize what you cannot measure. A common mistake among amateur builders is relying on feel, perceiving that a game feels smoother, or trusting basic task managers that lack the resolution required for true technical analysis. To achieve the performance levels we are aiming for, we must shift our perspective from a user to an auditor. The essential diagnostic toolkit. To perform a professional-grade audit, we rely on a specific stack of software that provides granular data. Firstly, WHEA-Info64 is non-negotiable. While many tools report temperatures, WHEA-Info64 allows us to monitor the effective clock of your CPU cores, individual voltage rails, and VRM thermal sensors. We aren't just looking at the average temperature, we are looking for thermal spikes, those millisecond-long bursts where your hardware hits a voltage wall and throttles. Secondly, latency serves as our primary tool for measuring system interrupt latencies. Even if your GPU and CPU are powerful, a background driver or a poorly configured system service can introduce DPC latency. This is the hidden enemy of the Australian gamer. If your system is spending cycles processing background noise instead of game frames, your 144 Hz monitor will never feel truly responsive. We use latency to isolate these interrupts and silence the background chatter of your Windows installation. Reading the event viewer, the hardware's narrative. Your operating system is constantly recording its own struggles, though most users never look at these logs. The Windows Event Viewer is a goldmine for the diagnostic-minded builder. Specifically, we look for WHEA-Logger, Windows Hardware Error Architecture entries. These are not merely crashes, they are warnings that your CPU or RAM is struggling to maintain data integrity under your current settings. When you see a WHEA-Logger error, your hardware is telling you that a specific instruction failed at a hardware level. This usually points to an unstable voltage curve or a memory overclock that isn't quite reaching the finish line. Instead of ignoring these, we treat them as signposts. If you are experiencing micro stutters, the event viewer will often tell you exactly which component is failing to communicate. This is the difference between guessing which part to replace and knowing exactly which setting to tune. The benchmark is a controlled environment. Diagnostics are only as good as the environment in which you test them. A casual game is too unpredictable to serve as a diagnostic tool. We use synthetic benchmarks, such as Cinebench for CPU stability and 3D Mark for GPU consistency, to create a worst-case scenario. We want to see how the system behaves when it is pushed to 100% capacity for a sustained period. During these runs, we observe the performance cap reasons reported by your monitoring software. Is your GPU hitting a power limit? Is your CPU hitting a thermal limit? Or is the system voltage limited? By recording these metrics, we establish a baseline. Before we change a single setting in the BIOS, we must know the exact behavior of the system under stock conditions. This baseline is the only way to prove, with cold hard data, that our optimizations are actually yielding results. Data-driven decision-making. The shift to a data-driven approach is what separates a standard PC from a high-performance machine. When we look at frame time graphs, we aren't just looking for high average FPS. We are looking for the 1% lows. The 1% low is the frame rate of the lowest 1% of your frames, and it is the true metric of smoothness. If your average FPS is 100, but your 1% low is 20, your game will feel stuttery. By auditing our hardware, we identify the hardware bottlenecks that cause these 1% lows and systematically eliminate them through precise voltage and latency tuning. In the next module, we will take the diagnostic data we've gathered here and apply it to our voltage curves. We are done measuring the problem, it is time to start building the solution. This ebook has 38 pages and its sections are very specific, which helps with any problem, maximizing performance. If you're interested, the link to buy it on Telegram with crypto for your convenience is in the comments. Without further ado, let's continue. Advanced Voltage Calibration, Mastering the V/F Curve. Welcome back to Core Logic O. If Module 2 was about identifying the bottlenecks, Module 3 is where we systematically dismantle them. We are moving into the realm of advanced voltage calibration. Many users fear the word voltage, but in 2026, voltage management is the single most effective way to optimize your system's performance per watt ratio. Our goal is to achieve the highest stable clock speed at the lowest possible voltage. The philosophy of the V/F curve. Every modern CPU and GPU operates on a voltage-frequency V/F curve. This curve dictates that as you increase the clock speed frequency, the chip requires a higher electrical potential voltage to maintain stability. Manufacturers calibrate these curves to be extremely conservative to compensate for the silicon lottery, the natural variance in quality between individual chips. Your goal is to map the specific potential of your silicon and tighten the curve. When we undervolt, we aren't just reducing it, we are allowing the chip to operate within its ideal power efficiency window. A chip that runs cooler is a chip that can boost higher and, more importantly, stay at that high boost clock for longer without hitting a thermal or power limit. GPU undervolting, the precision approach. For your GPU, we start by utilizing the V/F curve editor in software like MSI Afterburner. The process is systematic. Establishing the base, run a stress test at stock settings to determine your GPU's maximum boost frequency under load. The offset, we apply a negative offset to the core clock. Curve flattening, we manually lift the frequency at specific voltage points. By aiming for a consistent frequency, say, 2600 MHz, at a significantly lower voltage, e.g., 950 mV instead of 1050 mV, we effectively cap the power draw while maintaining or even increasing performance. This is not about brute force, it is about finding the sweet spot, where the voltage is just high enough to prevent arithmetic errors during calculations but low enough to keep thermal output well away from the throttle zone. CPU Core Optimizer and Precision Boost Overdrive (PBO). For CPUs, particularly modern Ryzen architectures, we utilize Curve Optimizer. This is a more complex beast than GPU tuning. Each core in your processor has different characteristics, some are stronger, can handle higher frequencies at lower voltages, and some are weaker. The diagnostic phase. Use tools to identify your best cores. These are the ones that should receive the most aggressive tuning. Negative offsets. We apply a negative magnitude offset in the BIOS. We start conservatively, perhaps with an offset of -10 or -15, and stress test using high-intensity AVX workloads. The stability wall. If the system crashes, it's usually because the CPU requested more voltage than we allowed it to have during a boost cycle. We then adjust the offset until we find the absolute stability limit. This process requires patience, but the result is a processor that runs significantly cooler and boosts more aggressively across all cores. The golden rule of stability. The most critical part of this module is the definition of stable. In professional-grade optimization, a stable system is not just one that runs a game for an hour. It is one that passes multiple cycles of extreme stress testing without a single WHEA-Logger error. We test for thermal stability, sustained load over 30 minutes. Arithmetic stability, checking for calculation errors using tools that force the CPU to perform massive mathematical computations. Transient load stability, ensuring the system can handle the sudden power spikes that occur when moving from idle to 100% load instantly. By tuning your voltage curves, you are effectively taking control of the hardware's internal logic. You are no longer at the mercy of the manufacturer's safe but inefficient factory settings. You are dictating the performance behavior of your machine, creating a platform that is not only faster but fundamentally more reliable.